Oh, I should have started. Okay. All right, so let's start then with user documents and examples. So I'll talk about how to get at the documentation for Geant4. There's a lot of it, fortunately. And we have several levels of examples, so basic examples, extended, and advanced. And we do have user support. So there's several ways that you can get help, both with Lxr and Doxygen, and with our Harper News user forum. How many have been to the Geant4 website? About half. Okay, that's pretty good. So this is where you go first. And let me just go through the site for you a little bit. You will find 4 major areas. So applications are over here if you want to look at what people have done with Geant4. There are various things like medical, space, physics, high energy physics, and so on. This is the important one. This is user support. So this is where you'll find all the documentation, access to the forums, bug reports, things like that. Publications. So here's where you can go to find Geant4 papers and related Geant4 papers, as well as this is where we keep our validation plots. So if you want to see how well we're doing with respect to data, go here. And then this portion tells you about our collaboration. All of our members are listed here, also with their email addresses. So this is one of the few places you can go on the web where you can have an email address and you can send a question to a developer. However, we prefer you talk to the forum first, and I'll tell you how to do that. So up here in the right-hand corner is the user forum. And down here at the bottom are various events. So the current tutorial would be in this list, if it's coming up, the next Geant4 collaboration meeting, and so on and so forth. And every once in a while, we have some news items, and that shows up in this box. So this could be the next Geant4 release when that's coming out. So you have all of the information you need to stay up to date with Geant4. Now, let's suppose we've gone to the user support portion of the main page, and we come to all of the documentation guides. The first one, and you're going to find out about this immediately with the hands-on example, is the installation guide. So you go to the main page, the user support, and then item 8B. So this tells you everything you need to know about installing Geant4. What platforms are supported, and what software you need on your machine in order to install and run Geant4. Then we have instructions. So how do you install this using CMake? And finally, how to make an executable program. This is actually in the developer's guide, and I'll tell you about that. But these are the main steps you have to follow to get to installing Geant4. And we will go over that in the hands-on. Once you have done that, then I think the thing you will spend most of your time in is something called the Application Developer's Guide. This is where you should go if you're a new user to Geant4. It describes all the most useful tools. What do you need to run your application? In some cases, there's example code there for you. It tells you how to set up and run the simulation application once you have built it. And it really is an overview of the toolkit. So it's not intended to be exhaustive. You won't find everything here. But you'll find all the pieces that you need to put together your first application. If you want to go into more detail, then we have the physics reference manual and the toolkit developer's guide. Now, suppose that you've been running Geant4 for a while, you've become something of an expert. Then this is the guide or the documentation that you would want to look at. So, if you are a developer or know a lot about Geant4 already, and you're familiar with the functionality of the toolkit already, then you can use this guide. So it requires some working knowledge of C++. And what it includes is a description of the object-oriented design of Geant4. So why did certain pieces of Geant4 get put in the way that they are? We have the philosophy of the design changes when Geant4 was originally conceived. And, as happens actually quite often, people become experts in Geant4 and they want to contribute code. And so there are some standards and procedures that have to be followed so that what you write can conform to the functionality that Geant4 already has. So you may decide that you have a nice new solid that you've developed for the solid. It tells you how you can add that. You can maybe modify the navigator or add a new physics field or something like that, or a new physics process. So all of these things can be done, and before you start contributing code back to Geant4, you should consult this guide. And then finally, if you're interested in the details of the physics and where that all came from and the references that it's based on, then we have the physics reference manual. This keeps growing. It's probably about 400 pages by now and always increasing. But this is where we try to keep up to date all of the documentation for the theoretical basis of the physics code that we have, the models and the parameterizations that we use. So all of these things involve, to some degree, approximations, and so it tells you which approximations we've made. It also, in many cases, tells you about the algorithms that we used and how we do the acceptance rejection for sampling a physical process. We'll talk about this some more, but it tells you how we do the probability of the occurrence of the interaction, so a lot like the introduction to Monte Carlo that I talked about already. This gives you more details. And probably importantly, it's a reference for all of the toolkit developers to understand what the underlying physics is. Now, there are some gaps. You'll probably see some places that say to be implemented. That's always going to be in documentation, but we try to keep those to a minimum and we fill them in when we can. Questions about the documentation before I change gears? Okay. We have lots of examples. They go from very basic, so these could be applications that demonstrate the simple features of Geant4, and we will talk about these in the hands-on. So these basic examples are good places to start. If you run through all of the Geant4 basic examples and understand them, then you're ready to do anything else in Geant4. Once you go beyond that stage, we have something called extended examples, and this demonstrates a lot of the specific features of Geant4. For example, the detailed operation of the electromagnetic physics is treated very extensively here. And then finally, we have something we call the advanced examples. These are more complicated, and I like to call them real-life examples because a lot of them come from actual experiments who have contributed their code back to Geant4, and you can actually run their code. So each of these has a README file, at least one README file, and also some web pages in a lot of cases. So each particular example must, by rule, have some kind of documentation going along with it. Let's go through the basics. You're going to see this one very soon, basic example 1. So some very simple solids are generated, and they're placed with respect to one another. And it just does something simple like it scores the dose in a volume that you select. And it shows you how to implement some very simple user action classes. B2, example B2 gets a little bit more complicated. We add a magnetic field and something called parameterized placements. Makoto will tell you what those are. Scoring in the tracker using sensitive detectors. So sensitive detectors are going to be the basics of your detection system. You're going to have that. Shows you how to use one of the physics lists that we have developed within Geant4. And now we move on to example B3. This is a schematic positron emission tomography system. So even though we say that it represents something in the real world like PET, it's pretty simple. It's simple placements and rotations, some crystals for Geant4 scores. It introduces a radioactive decay source and uses a modular physics list for building physics lists. So I'll talk about physics lists in some detail later. Example B4 uses replica geometries and also multiple scoring methods. So we have many to offer, and you can add your own scoring, but this shows you how to change scoring methods. And then it introduces histogramming as well as antiples. So you're going to want to store your data in some kind of form, and a lot of people use antiples or root files or what have you. The last basic example is actually getting to be somewhat complicated, or at least detailed enough to be useful, and that is the double arm spectrometer. So we have a central magnetic field, a dipole field here in the center, and we send a beam through a set of analyzing planes, and it is bent in the magnetic field into a hodoscope and then a calorimeter at the end. So we have scoring in multiple volumes. You get to define user interface commands, and it uses 1 and 2D histograms to save your output. Extended examples. Okay, we have 20 of these, I think. And they go from, oops, there they are. Let me start here. So we have analysis, biasing, electromagnetic, run an event. This is a big one. So if you want to learn details about how to manipulate the run and the events within it, and I think this is where the time variation of you can put in time variation of your example. That's there. Here's a parallel processing example, optical physics. So let me go back a little bit more detail. So there are lots of electromagnetic physics simulations with histogramming available. There are hadronic examples. Biasing. So I mentioned that also this morning. This tells you how you can speed up your simulation with various types of biasing. And this thing called reverse Monte Carlo, which we'll talk about later. And there's a visualization example. So that's a good one, because there are a lot of options in visualization, and Mihaly will tell you about that, I think, in the next talk. But here's a good example to look at. So all of these, this is a good one. Here's medical examples. So there are many of these, and they're quite detailed. And optical, also very detailed if you want to do things with phototubes or wavelength shifters or scintillators or light pipes, things like that. Almost everything is included in here, so that's a very good extended example. On to the advanced. Now I'll spend some time on some of these. I think we have another 20 of these as well. But as I mentioned, these are real-life simulations. So experiments have used these for their data or their design and have contributed them back to Geant4. So the gamma ray telescope is here. And this is very similar to the Fermi Space Telescope, which is in operation now. And the idea is that it's selecting gamma rays from the sky and analyzing those. It's a set of 16 hodoscopes with calorimeters. So there are hodoscope planes here, tracking the particles. And then at the end, there are cesium iodide crystals that act as calorimeters. And there are 16 such towers in the telescope body. So it provides the physics to do the tracking and the calorimetry, and the physics list here is specialized for this particular use. It's called Gamma Ray Telescope Physics List. It has its own particle generator and uses AIDA-based analysis, so quite a complete example. Makoto mentioned this, the X-ray telescope, so he told you the story about why this is important. But the code is there, so you can actually run this and see that, yes, protons really do destroy CCD cameras when they're focused. So I won't go into too much more detail here, except to say that all of these things are available. So the geometry is there for the carbon fiber tube and the X-ray focusing mirrors, and multiple scattering is set up. So this is a particular type of multiple scattering. G4H multiple scattering deals with hadrons. So we have a specialized multiple scattering which deals with hadrons as opposed to the one that deals with electrons. Underground physics is kind of a broad category that would include things like dark matter searches, which are in deep mines, or rare decay experiments where you need very low background and have to make sure that you're in a mine so that the cosmic rays don't get down to you. When you're doing low background things, you need a realistic representation of your environment. And so in this particular example, the entire laboratory is designed. So this is basically a lab area with desks, windows, lots of things, anything that may be a radioactive background. So you have to find out what would be the radiation coming from the walls. It has full lab geometry, so all of this is there. For example, if you have neutrons which are produced by cosmic rays, then you have to do the high precision tracking of the low energy neutrons. Physics here is the standard electromagnetic. We also have a package called low energy electromagnetic, and Mihaly will talk about that in detail. High precision neutrons, which I just mentioned. Very important here is the optical processes. So as part of this example, you have a detector, which is a photomultiplier tube looking at some xenon. And it's a two-phase xenon detector. Part of it is liquid, part of it is gas. And so you have these optical photons that propagate through the liquid phase and then out into the gas phase, and you have to simulate all of that. So all of that is done, and this shows you how to do it. And then, very important, because it's a low background experiment, you have to simulate all of the radioactive decay that can go on in the walls or in your detector or with somebody eating a banana. So, you can't go down into a mine if you just had bananas the day before because they have a lot of potassium-40. It's true story, really true. So you have to simulate that. Hadron therapy. Our collaborators at INFN in Catania, in Italy, developed a system for simulating the proton beamline for eye treatments. So here is what the people in the medical field like to be polite about it. They don't call it a person or a target. They call it a water phantom. So this is your person. Here it's just a box of water. But the beam comes in here, and then it comes through several analyzer planes and things like that. And the beam then goes into some phantom, which is supposed to represent the material of the eye. And so protons and ions are sent in, and the beamline is simulated. Standard geometry for this is now used for the IAEA benchmark for this type of studies. And the physics is reference physics list developed by Geant4. And this uses the ion-ion interactions, which are quite useful for medical applications. More radiation protection and background. We have things called Anthropomorphic Phantoms for Geant4 simulation. So if you want to find out what kind of a dose an astronaut is getting, for example, or somebody, a radiation worker, then they have, in this case, it's a fairly crude model of a human, but good enough to give you an idea of where the radiation dose is coming for a given background. And this is something, at least you can see intuitively, how you might build this up with simple Geant4 pieces. So for that reason, it's kind of nice to see that, yeah, even at the simple level, you can represent organs and ribs and lots of materials in the human body. So it has something called an MARD and ORNL, Oak Ridge Phantoms, and there are male and female versions for each one. And all of these geometries are implemented using GDML. So 20 advanced examples. Here's a good one. This is from the AMS experiment, so looking for antimatter. What's another good one? The DNA physics. Makoto mentioned that we have DNA processes in Geant4, and you can do lots of things with simulating not only the physics going on, but the physicochemistry part. And it actually is quite detailed. Lots of things for medical. So gamma knife, hadron therapy, ion therapy, medical LINAC, all of this stuff is used for doing either dose planning for radiation treatment or developing treatment heads for particular devices, cancer treatment devices. and I mentioned the underground physics, X-ray fluorescence, X-ray telescope. So lots of different examples to choose from. Just have some fun one afternoon and go through these and see if you find one you like. Questions about the examples? I'm changing gear again here. Okay, we have a general rule in Geant4 that sometimes people want to contribute examples. We require them to promise that they will be around for a few years to maintain them. Okay, we don't just want examples of Geant4 that get put there and then get left, and then nobody pays attention to them. So these are all active, running, good examples to look at. So, user support. Let's suppose that you're now diving into Geant4 and you're starting to look at the code. Now, the first time I looked at Geant4, I was very confused about where things were. And so we didn't have this tool then. So now it's a lot easier. Lxr Code Browser is developed and supported by our colleagues at KEK. And you can basically just search the entire Geant4 source tree by typing in a file name. So if you know what the class is that you're looking for, like G4 track, for example, type that in, and you'll get the information on that. You can also use some identifier. So you might use G4 box if you want to find the code for how the tracking in a Geant4 box is developed. Then you would put that in. Or just some text string. So you can search on all of these. What you get when you do that is a linked source to both the classes and the methods. So you can drill down into the code at whatever level you like. You can find out all the information about the coding. We do also have a Doxygen version of this. So you can look at some PDF output if you want to by going to that. And here's how it would look. So if you actually go to the Lxr Code Browser, you'll see a page that looks something like this. And in this case, I've done something simple. I've just started to look at alpha particle. So I typed in G4 alpha, and then I got this class diagram. Okay, so that's really pretty simple, but you can already see a little bit about how Geant4 is designed. So we have G4 alpha is derived from G4 hadron, and that's derived from G4 particle definition. So this gives you a little bit of the class structure. And then all of the member functions are listed, so you can go into each one of those. And also the attributes of the class. So if you're looking at the C++, then you really want to go look at this browser. Finally, we have a Hypernews forum. This is maintained at Slack, and it's been around for a long time, so we have a lot of questions that have built up. But this is your chance to ask questions to experts of Geant4, or once you become an expert in Geant4, to answer them yourself. So this is what we really hope. People learn Geant4, they start answering questions on the forum. So as I mentioned this morning, you just go to the top of the Geant4 homepage, so it's up in this corner. Click on that, and you'll come to the forum. So this is where you can do discussion, post your questions, and so on. So there are 23 separate fora divided according to category. So there's a hadronic physics forum, there's an electromagnetic physics forum, there's a medical forum, lots of them. Just go to that page and see what's available. We have actually also 4 forums for specific application areas. One of these is medical, one is space. I think we even have one called educational, and I think even an industrial one. So if you happen to work, one of the companies that uses Geant4 is Tetra Pak. And they make the milk cartons, and they do radiation treatment of the milk cartons. And so that would be an example of somebody in an industrial area using Geant4 could post questions. So we encourage you to look at this, especially if you run into a problem. Please go to the forum first, because probably somebody has asked your question before you. Go through it, and if nobody has asked that question, then please go ahead and enter. We'll be happy to answer as soon as we can. It's a best effort basis. Everybody in Geant4 usually has at least part-time other job. So we're not full-time on Geant4, and we answer the questions as we have time. So you might not get an answer right away, but we're pretty good at keeping up to date. So please join. You'll see this new member at the top of the page. So click on that, fill out the form. There's a little box down there that says add some comments. So it would be nice if you said, I was at the São Paulo tutorial. Then when I'm looking at this, I can say, yeah, I don't have to check this person out anymore. I know he's okay. So that's it. And we've talked about installation, application, toolkit, and physics guides. So these are our main documentation in Geant4. This should give you just about everything you need. There's obviously more than you need here, but it's pretty complete. We have 3 levels of examples, so you'll be seeing a lot of the basic examples in the next week. Extended examples if you want to start getting deeper into Geant4 and how it works. And then real examples or advanced examples. So you will eventually come to the point where maybe you'll find an example that does pretty much what you want to do. You can just copy it out and use it. And then user support. So we have cross-reference code browsers, user forum, and periodic tutorials. So that's all for me. Are there questions? Yeah, okay.
Okay, so let me repeat that before I start. So if you have any installation issues, please fix it before the hands-on session this afternoon. Okay. Today at hands-on session, we expect each of you to try out at least a couple of examples Dennis just mentioned to check if everything is okay. Okay? And it will be too late for you to start installing Geant4 at that time. So finish installation by then, okay? And this particular talk of interface 1, user interface 1, is guide you how to interact with Geant4 application. That is essential to try out our even most basic example, okay? So, it starts with the command syntax, then macro file, and G4UI executive. That's something you see. So UI command. Each command consists of 3 parts, directory, command, and parameter. This first part is directory. But directory could be more than one level. Okay? It's really like a Unix directory structure, okay? And command itself, that's shown in green. And depending upon each individual command, it may take 1 or more parameters, okay? A parameter can be a type of string, Boolean, integer, or double. And space is delimited, okay? And if you have a string that you have to type in as a parameter, and that string has a white space, then you may use double quotes that make these words into one string. Okay? A parameter may be omittable. If it is the case, a default value will be taken when and if you omit the parameter. Okay? Default value is either a predefined fixed value or a current value, depending upon each individual command. So when you type help to the particular command, it always say, if there is a parameter, of course, if that particular parameter is omittable or not, and if it is omittable, what is the default value? Okay? And if, for the case of the command that takes more than one parameters, and if you want to use the first parameter, the default, but you want to specify the second, you cannot simply write the second parameter because then it will be taken as a first parameter. So use the exclamation mark here as a space holder. That tells that to Geant4 that the first parameter is something you want to use as a default, but you want to specify the second. Okay. Now, command submission. You can issue a command when Geant4 is running in interactive mode. So there's a prompt waiting for your input. Or if you have a nice GUI, there's a window where you can type in a command. Okay? Or you can write your command in a macro file and Geant4 can read it. Okay? And also, if definitely needed, you can hard code in your source code of your user application code to say use this command or read this macro file. You can do that. It's very handy, very useful because compared to any other C++ method invocations, you don't need pointer. Just say to the UI manager, run this command. That's it. But please, don't do it in an event loop or deep inside the event loop because as you see, it's string manipulation. If you do it for every track or every step, it just destroys the performance because every step we have to read the string, have to understand what's going on, and do something you want. It's slow, but still it's very useful. If, for example, you want to set a default value, that will be done only once at the beginning of the program. It's very useful. Okay, so yeah, basically, when you write any code for Geant4, please keep in mind how often that particular line or that particular method is invoked. If it is invoked just once in the program, you don't need to care much about the performance. But if it is invoked more than quite periodically, per step, per track, you really have to be so careful. Avoid, for example, sine, cosine, exponential, pre-calculate it, otherwise it wasted your time. Okay? And so is this string manipulation. It's the biggest killer. Okay? Even Atlas, they check particular name for every step. I jumped up when I found it. They complain Geant4 is slow. Of course, they checked particular name and volume name of 40 character long every step. It's wrong. Okay? So please keep in mind what you are doing, in particular while you are doing something per step. Okay? Anyway, let me come back. The availability of the individual command, the range of the parameters, the default value, everything depends upon your application. Okay? For example, there's a famous command, gun/gun/particle. That is a particle gun command to specify what kind of particle you want to shoot. But in your physics list, for example, if you don't define proton, you cannot shoot proton because you don't have it. So everything is variable, depending upon your application. Okay? So command could be diffused if it's in a wrong application state. For example, if Geant4 is already in the event loop and you want to change the production threshold, we say no, it's too late. Do it later after run is over. You can proceed to the next run with different fresh cuts off. Okay? So on and so forth. And wrong type of parameter. While Geant4 is expecting integer to come, if you type ABC, we say no. Okay? And insufficient number of parameters, if parameters are not omittable, and parameter out of range, of course, if it is allowed only from 0 to 10, and you say 100, we say no. Okay? And for the case of integer or double type parameters, and parameter out of its candidate list, for string type. So if you say proton, but if you don't have proton in your physics list, we say no. And of course, if you make a typo of the command name, we cannot do it. Okay. Now, macro file. Macro file is an ASCII file. You can edit, of course, and that contains UI commands. Okay, one or more commands. And all commands must be given in the full path directories. As we said, there are directory structures. In the interactive mode, like Linux, you can change your directory, CD something. But for the case of macro, we cannot assume which working directory you are on. So when you write a command in macro file, you always have to write full path directories. Okay? You may use pound mark for the comment line. Whatever the characters after first appearance of the pound mark will be ignored. And in addition, if you set control verbs to up to 2, this comment line will be echoed back to your display. That makes a lot of sense if you want to know where your program is going. Okay? And macro can be executed. Macro file can be executed interactively when you type this command, /control, /execute, and macro file. You can even add Unix-like directories, even if you are using Windows. You can use Linux-style directory structure so that the macro file should be one level up or whatever. You can do that. Or hard-code it. Get UI manager pointer and apply command method. And here, the string. This is exactly the same as this one. Okay? And this is particularly important if you want to set any default values. So create a macro file that defines all the defaults. And at the beginning of your program, read it. Read it means execute this command with your default value macro file. Okay? And in the interactive mode, if you type control manual, it dumps out all the commands available on your screen. Or if you specify command directory or subdirectory, it dumps all the commands in that directory. It's almost useless because you found maybe thousands of commands. But instead, you may use this control create HTML. This will actually create HTML files of all the commands. This is not only the commands Geant4 had already defined, but also the command you define. And I'll discuss later in my user interface 2 talk how to define your own command. It's essential for when you create your own application. You want to use some UI command to change something. And in particular, if you let your user use your application, instead of writing manual, it's always hardest thing to do. We agree. Just run this command. So it will create a nice HTML file so that your work for the writing manual is done. Okay. And actually, in our user's guide, for the section of the UI or the UI commands are actually automatically generated by this command. So we ourselves use this command. It's useful. Although format is quite ugly, I agree. Now, alias. Alias is something quite similar to the environment variable, or alias actually, in Linux. Okay, so you can set control alias name and value. Okay. Alias is also set with control loop and control for each loop commands that I'll describe in my next slide. And please note that alias value is always treated as a string here, even if it's just numbers. Okay? And alias value can be used in the other UI command with a set of curly brackets. For example, control alias TV, it's the alias name, and this is string. Okay, then you can just type set of curly bracket TV and 1. That will be interpreted as this string. So you can shorten the long command if you like. But more important use case is here. The first is alias file1. File1 is the alias name, goes to this particular data. Next alias is file2, goes to the other data file. Then alias run, this is alias name, set to number 1. And we interpret inner pair of the bracket first, so that this run comes to number 1. Then this string comes to file 1. It means we get file number 1 rather than 2. So depending upon run number, you can read different file. Okay? And also there are some simple mathematics, add, subtract, multiply, or these kind of things in the macro on alias, so that you can really do some more intelligent things, okay, by macro. Now loop. We have 2 loop commands, control/loop and control/for each. Loop is used for numerical looping, while for each is to be used for strings kind of looping. The first one, loop, takes macro file to be executed, counter name, into variable name, I would say, and initial value, final value, and step size. So this is the sample. Control loop myrun.mac, kinetic energy 10, 20 is the maximum number, okay, and step. So by this command line, you can execute myrun.macro file 6 times, starting from 10, 12, 14, 16, 18, 20, okay, 6 times. And in myrun.macro, there's only one line in this macro file that says control for each. My single run.mac, this is another macro file. This is a variable, and here's the options, proton, pi minus, mu minus. By executing this line, it executes this my single run.mac 3 times with different particle name. And given this is executed within this loop, so different kinetic energy. So by executing this one macro, you can actually execute 3 times 8, 3 times 6, 18 different runs with a combination of different particle type and kinetic energy. Okay? Got it? Now, batch mode and interactive mode. You can run Geant4 in either interactive mode or batch mode. The only difference is if you instantiate G4 UI executive. Don't ask me what this executive means, I don't know. Anyway, and if you say to this executive guy, session start, it comes into the interactive mode. Okay. This UI executive will instantiate whatever the best GUI option you have in your installation and run it. So you will see the command prompt or the input field to type the command. Okay. If you don't instantiate this, you are in the batch mode, so that you can still apply command with the control execute to run macros. Okay? If this is the case, there is no terminal, so you cannot type in anything. Geant4 will run what you ordered in your macro file and finish the job. Okay? Now, in terminal commands, if you use G4 UI terminal, it's exactly the same as what you can expect in your Linux terminal. You can change directory, type the current working directory. You can type ls. And if you are C shell, not TC shell, but C shell, good old days, you can type history to see the command line, command ID, and use exclamation mark to use that particular command. And arrow always works, going up, going down the history, or going left and right. And you can use tab. Okay? And one thing that is completely different and from unique and quite unique is question mark. If you type question mark just in front of a command, it tells you what is the current value. Okay? If you want to know what is the current value of that particular command, just type question mark. Okay? And help always works. If you type just help, it starts with the help menu so that you can go down to any directories if you like. Or you can type particular UI command. Then it will tell you the guidance. Okay? And once you type exit, the interactive job is terminated. Please note, these are only for interactive mode. You cannot type, for example, help in your macro file. It doesn't work. Okay, that's it. Questions? And I do expect you to try some of these commands, maybe in the macro file, with a couple of examples this afternoon at hands-on. Once you succeed, you realize Geant4 is not difficult at all. Actually, I can safely assure the most difficult part of Geant4 is installing it. And installing Geant4 is not difficult whatsoever. The only difficulty comes with GUI, Qt, or different compilers. They make all the complications. Geant4 itself is easy. Okay, question. Okay. Let's see if it works. It's working. Just say yes or continue. No, just say click OK or delete or you don't need anything.
It works as well. Yes. I like the old things. So I will say a few things about visualization. A bit of connected to where Makoto finished with the batch mode and interactive mode and graphical user interfaces and so on, because you will see some graphical user interfaces, but I want to make sure that you make a clear difference between visualization, the visualization window, and the graphical user interfaces. But before I start, then if you think a bit about visualization and detector simulation, immediately there are many things that you want to use visualization for. So some would like to show their detectors, some others would like to show their trajectories, particles. Some would like to show all these things in a static mode. Some would like to rotate, zoom in, and do some other tricks, even movies about it. But sometimes you need a very high-quality image for a publication, poster, or technical report or something. or you want to access a complex detector and you would like to work in the detector hierarchy, especially through the web. So you can see immediately there are many, many different requirements regarding visualization, and there is no one visualization driver that can fulfill all these requirements. Okay. But one other thing before I go into the visualization, that you will see things this week that are essential to do your simulation. Okay, visualization is not essential. You can use visualization, as I mentioned, for many things. And you will see today what are these things and what are the best drivers for the special requirements. And I will talk about several drivers, and I will show some images. We can start immediately to list them, like HEPREP, OpenGL, down, Ray Tracer, Open Inventor, GMOCRAN, and other HEPREP. And what you will see most of the time, and we will talk about this, is a combination actually of OpenGL in a Qt graphical user interface. But again, a difference is this is the OpenGL visualization window embedded into the graphical user interface, which is the Qt part. So, as I mentioned, there are many things that the user would like to visualize. So what is possible to visualize with these drivers that I will mention? So, of course, there are some data that's directly connected to your simulation. This is the description of your simulation, which includes your detector. And I must say that actually whenever I use a visualization at the very beginning, when I started with Geant4, you will see there are 3 lectures on geometry, how to define your geometry in a C++ code. So at the end, you would like to see whether everything looks as you imagine. So indeed, you can use visualization to visualize your geometry. And this is most of the time when I'm using, for example, visualization. But of course, after you visualize your geometry and you have your particle gun, you can even shoot the particles and you can draw the trajectories and so on. So you can, of course, visualize trajectories and the stepping itself. You can and you will, in the hands-on, you will see that you can visualize even what you are doing the visualization for. For example, if you are collecting some energy deposit in different parts of your detector, you can put into visualization these things as well. These data are directly connected to what you are doing with the simulation, but there are also some other additional things that you can put into your visualization skin that can help the visualization. These are polylines, which means that connected line segments, like this 3D coordinate system, that you just put into the origin, and when you rotate your geometry, it helps you for the orientation, for example. But you can put other 3D markers, but you can also write some text into your visualization. And since 10.4, we have even nicer documentation than before, in general, in Geant4. And the visualization section is very, very nicely documented with all the details. Okay, much more that I will cover today. And this is actually here, it's a link that brings you directly to the visualization section of the documentation. So if we want to put into a table all these requirements that I was mentioning, here, as you can see, that high quality printing, interactive, and so on, versus the different visualization drivers, then we can see that there are no one drivers that would be green everywhere. Okay, this is what I mentioned. But you can see that OpenGL, together with the Qt graphical user interface, can do almost everything, except it does not support browsing your geometry, for example, through the web. But there is another driver that via RML that supports this one. So this is, again, from this table you can see that according to your need, you choose the visualization driver. The good news is that no matter which driver you will use, your code do not change at all. This is, again, a nice thing of the using object-oriented languages, that interfaces are defined and the drivers are implementing those interfaces. Okay, so the code do not change. On the top of this, actually, you can do visualization directly from C++ code, so you can write the C++ code to do some visualization, or you can use user interface commands that Makoto was talking about, special viz in the special viz directory to do some visualization. Depending on some other dimension, we can divide the available drivers into different groups. Here you can see one division, depending on whether the visualization is happening or is connected directly to the Geant4, so everything is done from Geant4, or first Geant4 need to be run, it will produce a file, then you will take this file offline and will do the visualization. So the first category, we can call it interactive if you want, OpenGL, Open Inventor, Ray Tracer, and ASCII3. And ASCII3 is special. We will get back to this at the end. And the others will need to require first Geant4 run that will produce a special file format. Then we'll require a file browser that will load this file and show the geometry. I will show something like this soon, so it will be clear. So there are many drivers, and as you could see, and some of them will be always available. Whenever today or before this tutorial you install already Geant4, you can see that there is a long list of drivers that are available immediately. This is because it's not, these drivers do not require to have any special libraries installed on your system, so they will be there immediately. Some other drivers, like for example, you cannot see here OpenGL and Qt and these kind of things that are the best that we can give today. It's because they require Qt installed on your system, for example, and the GL library for OpenGL to be installed on your system. But then, if you want them, you need to specify that you want your Geant4 build at build time, actually at CMake configuration time, with a special CMake flag, that you want to build your Geant4 with Qt support, for example. And Qt will immediately require GL for OpenGL, okay? So if you just build Geant4 and you try to run visualization and you see some error messages, then it's very likely because some drivers are missing or something, okay? So if everything, if your Geant4 was installed with OpenGL support, Qt or X11 window, then you can write actually this two simple command to show your detector after the initialization. I mean, after the Geant4 initialization, when your detector is already created. With open OGL, OGL refers in this case to the visualization driver that is OpenGL. It could be any of the others if those are available. And the second line, draw volume, will draw your detector as it is. Now, you will see this this afternoon and tomorrow. During the hands-on, you will see commands like this. I think there will be a second visualization lecture a very short one, 20 minutes, I will list tons of visualization commands. Okay, it's nothing, just one command, the second, third, till 60 or 70 different commands. And I will explain what they are doing. But each of the examples, practically, that comes with Geant4, and Dennis was talking about them. If you go them into the directory, into the subdirectory, you will see some macro files to run in batch mode, the example, and you will see some viz.init and viz.mock files that are visualization macros. These files will contain several visualization commands, very likely starting with viz.open, and will require some of the visualization driver, and setting up the position of the visualization window, the size, and so on. Then drawing your detector geometry, adding some tracks, changing the view, and so on and so on. So if you go to the example and look into the viz.mock file, you will see immediately many visualization commands. So we will run through all these visualization drivers, but we will say only a few words at each of them, and I will try to show something, how the visualization looks if you are choosing this or that driver. The first one is actually, it's not only the visualization driver, but because the visualization driver in this case is OpenGL, but it's the OpenGL together with the Qt graphical user interface, okay, which is the probably the best in general, okay, in general the best that we can do. It doesn't mean that for your special needs this will be the best, but statistically speaking this is the best. This is because the recent development was focused on this combination. And how it looks, you don't forget that this is not something that you get with your Geant4 build. You need to specify when you are building Geant4 in the CMake phase that you want to build Geant4 with Qt support. Okay, then it will be done, and then you run the example. This is B5, basic B5 example that Dennis was just mentioning before, and this is what you will see. So you see in the middle the visualization window, and all the other is the graphical user interface. Without visualization support, it would be exactly the same, but you would not see anything here. There would be some text description about this example, the README or whatever. No, this is the session part where you can type your commands, the user commands that Makoto was mentioned. You just type here /run /initialize /run /beam on, and you will run the simulation. Initialize and run the simulation. Now the output, the text output of the simulation will be printed out here. Okay. This what you will see if there is no any visualization. You are running with TC shell, for example, terminal. Then you write the same things: /run /initialize /run beam on 10. Then you will see only this text output. Okay. Then other parts, as I mentioned, this is the visualization window. If you want, you can open more than one tabs, and you can switch between them. You want to plot here or plot there some other things. And you can control the visualization window. From here, you can see a toolbar that will connect the graphical user interface, the Qt graphical user interface, to the visualization window. So this is why you can control, in this case, the visualization through the user interface, because you have some tools. For example, if you click here, you can zoom with a click. Then you change to this tool, which will allow you to rotate this whole geometry with your mouse. Okay. You will try it today, tomorrow, or this week by yourself. In this way, you can zoom into a part of the geometry, you can rotate, you can check whether everything is really as you imagine when you type the corresponding C++ code. You check your geometry, for example. Now, this tab contains 3 subtabs, and the most interesting is this help one, which lists all the available command directories, and within the directories, all the available commands. Moreover, if you click on one command, you can find the help description that Makoto mentioned, that each command has a description that with the help that shows what are the arguments, okay, what type of the arguments are required, and what is this command, okay. The other 2, one will be the history, the commands that you have executed so far, and there will be the third one is connected to the graphical user interface again, for the visualization interface, and it will allow you to decide which part of the detector hierarchy you want to visualize. Okay, if you compare the previous image, this one to this, we removed some part because we want to see only some special part of the geometry. And here, with few clicks, you can achieve this and even more. So that was OpenGL combined with the Qt graphical user interface. But as I mentioned, you don't need Qt to have OpenGL visualization. You can have OpenGL visualization with X Window 11 support. Then you can do visualization as well, but you will have only this window when you are running. You will do everything on a terminal, okay? Then you will have an additional window where your visualization will be shown, okay? But then here you cannot use your mouse just to go there and rotate or zoom and so on. Each operations like this, you need to write the corresponding command by yourself. Okay, so it's a bit, you have all the power, but it's not as user-friendly as with the graphical user interface. Okay, but it can do all the things. You can see that it will give you high-quality photorealistic image. It will give a fast response, which means that if you rotate, it will rotate it immediately because it will use the full power of your graphics hardware. You can output with very good quality images if you want to put into small pages, publications, and so on. This is perfectly fine. Moreover, you can do even movies with this OpenGL that I will get back at the very beginning, very end. OpenGL and Qt is not the only combination to have OpenGL control the graphical user interface. But the Qt is much more advanced than this motif graphical user interface control. But you can still try, it should work. Okay, but you get much more with Qt compared to this, but they are quite similar. As the Open Inventor view, here we are not talking about anymore Qt, anymore OpenGL. Okay, it's Open Inventor, and it's quite similar to having a motif or Qt with OpenGL. Okay, you have some graphical user interface control, and you have the visualization window, and you can control the visualization through some graphical user interface. And if you see, it will give you quite the same characteristics as before I was saying, photorealistic image, some interactive features, zoom, rotate, and so on. But you will need to have Open Inventor libraries, which are installed on your system, but they are available freely. And you can find, each time I put the direct link to the documentation of this part. Okay, you just click there if you are interested, and you find even more information on Open Inventor. The same for HepRep, and HepRep is already the first one in the list that doesn't work directly, the visualization not happening directly when you are running Geant4. Okay, first you need to run Geant4. with a HEPREP file driver that will produce a file. It's either in this format or that format. The important is that after you need to have a special browser for this, that you can see if you were running with this HEPREP file that's produced an XML file with HEPREP1 format. Okay, these are not very important. The concept is important here. Then you need to have this HEP-ROP application that you will. This is shown here. Okay, this is already the HEP-ROP application where the file is already loaded into this application, so you can see the visualization here. Okay, offline if you want. And with this HEPREP, as you can see, the produced image is not as nice as with the OpenGL because it's more a wireframe, simple visualization, for example. If we go further, and we will see more and more specialized drivers like the down file. That again will produce, when you are running Geant4 first with this driver, it will produce an output file. Then this output file is taken and the visualization is done by down, and it can create the highest quality image. So if you want to have an image to your poster, for example, or into a technical report, then this is what you are looking for, down file, because this will give you the highest quality image of your detector that is available. On the same time, the file that's produced here, this .prim file, can serve as an output to two other programs if you want, downcut and David. Downcut can make a planar cut on your image and producing an additional file, okay, the output of this cut. Or what is very useful in case of complex detector is checking overlaps. Overlaps are mistakes that you did during your geometry, okay, that you didn't put properly your volumes, but somehow they are overlapping. And you can use this kind of visualization, Dawn and David, that will take the first file and will produce a second file where the overlapping part of the geometry will be highlighted like this. Okay, so it's very useful in case of complex detectors. VRML, this is again, first you will run Geant4, it will produce a file. The specialty of this driver is that this is the only one that allows to browse your detector view through the web. Okay. Again, if you would like to see about this, you can find the documentation here, but this is the most important point with this driver. Ray tracer, the specialty of this driver is that this is the only one that will use Geant4 tracking. It's ray tracing, actually, which means that the image is produced in such a way that simulation is done, but with the non-interacting photons, if you want. So it will, particle will go through boundary to boundary, and this is how the image is created. And this is the only image that can handle all the geometrical shapes in Geant4, including even Boolean solids. Okay, and what you can see that it provides, for example, shadows, as you can see on the first plot, and also transparency. And you can find more information on this if you click on this ray tracer documentation. And another version of this ray tracer is the ray tracer X, that's doing everything, rendering the image on the fly, if you want, and showing you on the fly. Like ray tracer will run, and at the end will show you something, and whether it's fine-grained enough or still you need more event odd to have a finer image, you will decide at the end. Together with this ray tracer, you can use both, and this will immediately show you can see at the beginning there are no enough events. With more events and even more, there are better and better the resolution of the image. And you can see when it's fine, you just shut down everything and you have the proper image in your hand. Gmocron, this is a special visualization driver for volume visualization, as you can see this example, and this is popular in case of medical application when you need to visualize the body, or in this case a head of the patient. Sky3, this is a special one because it's not visualization. Actually, it's visualizing your geometry hierarchy in a text format. So it will print out your geometry hierarchy, as you can see, like this as an example, in a text way. Okay, but you can do special things with this Sky3. That, for example, it can calculate the weight of your detector, okay, or the volume of the detector, even including subparts of your detector and so on. As an example here. Now, at the very end, just to show something interesting, how useful that you can decide, in some case might be very useful, you can create movies with Geant4. You can find the documentation here, and under this several links, some how-tos if you want to create something like this. For example, where you can see a 10 GeV pion going into a calorimeter. And each particle type has different colors, and this is one event visualized from the beginning till the end. And with the version 10.5, you can even narrate this. So if I have actually a version, if we go just further, I will show at the very end. So I put one slide here with all the other web documentations for the different drivers. You can click there if you are interested in this or that driver, that will find even more information. What you can expect different web pages here dealing with the different drivers, like this is the HEP rep, this is for the down file, and this is for OpenGL, and this one is a special Qt plus OpenGL. So you go there and you see all the details, visualization, commands, and so on. So before I show this movie with the narration, I just would like to summarize that, okay, we saw that there are many, many drivers, and the most important thing is that, first of all, this is not essential for the simulation, but can be very useful. And if you find it useful, then first you need to decide what you want to use visualization for. Then you can choose the proper driver, okay? So let me try. I'm not sure that you can hear anything, unfortunately, because we don't have audio contact. But this is a movie where actually you can not only see what's going on, but somebody is narrating and telling you what's going on. Okay. If you are interested, you can go to this link here, where John Allison has even more collection of movies like this. That's all. Any questions? Yes? Qt, you just install Qt on your system, and that's all, yeah? Without any. On Mac, I'm not sure, Makoto might know more about it, that the recent one, there are some problems. That's true. What I'm not sure, but I heard something that in the latest Mac OS X there are some difficulties. Yeah. Okay, so that's it. I think it's lunchtime. Yes.
Thanks for all the lectures, and it's 12:30. We should come back in 1 hour and 10 minutes. Okay?